Now we want to look at weirder indeterminate forms, right? We've seen we can use L'Hopital only with quotients, right? It has to be a quotient top and bottom and has to be of an indeterminate form 0, 0. However, there are some indeterminate forms that aren't even related to quotients at all, like these two, infinity times 0 and infinity minus infinity. These are indeterminate forms, right? Sometimes we have to handle these forms by using like some kind of algebraic manipulation to make it look like 0 over 0 or infinity over infinity. So we have to use algebraic manipulation with these types of indeterminate forms, right? I'll just write it here. Algebraic manipulation to get to an indeterminate form that we're more comfortable with, right? These two. That's a bad infinity sign. Right? These two. We use algebraic manipulation for these specific indeterminate forms, and we want to try to get it to this, right? Not too difficult to think about, but it might be difficult at first. So we're going to look at two examples, one of each. Alright, this one is a very interesting problem because when we plug in x equals infinity, what do we get? We get infinity times what? Sine of 1 over infinity. That's kind of like sine of 0. Sine of 0 is 0. So this is indeterminate form, right? Indeterminate. But we cannot use L'Hopital's rule right away, actually, because it's not in a quotient, right? We can only use it in a quotient. We can't just simply find the derivative of the factors of the product and then just evaluate the limit, because that's not what L'Hopital will say. This one's a particularly interesting one because we want to make us use algebraic manipulation somehow, and I guess it's kind of weird looking at this 1 over x, so I kind of want to redefine this, right? Let's make a number h such that it's equal to 1 over x. This kind of helps in some way. This will probably be this is going to lead us to the solution, right? So if I do this, we actually have, so I'm going to leave what's on the bottom alone. Well, x, what is x equal to? X is equal to 1 over h, isn't it? 1 over h, and then sine of what? H. So I left the thing at the bottom of the limit different because we're actually changing it by making this substitution here. Let me bring it right here. This is where we should focus. So when I make h equal 1 over x, right? As x goes to infinity, what does h go to? It goes to 0, right? It goes to 0. So that's why we have to make it h goes to 0, right? Specifically, we have to make it approach from the right side because of the substitution. We are only focused on it approaching on the right side because of that substitution that we made. So that's the idea. When we make that substitution, we might have to change our limit, I guess, inputs, if that's what you want to talk about. So now we just look at this. Now it's just a limit as h approaches 0 from the right side of sine h minus h. And we've done this problem many times before, but let's actually plug it in. We get 0 over 0. This is indeterminate, right? Indeterminate. Now we can use L'Hopital's rule. So it's now the limit as h approaches positive this of sine, or the derivative of it, cosine of h over 1, which is equal to what? We plug in 0 to cosine and we get 1. So therefore, this limit right here is just simply equal to 1. So that's the answer. Using L'Hopital's rule, we just found the answer. Using a substitution, this is like a type of manipulation you might have to use. And remember that we have to re-evaluate what the limit is, and it's from the positive one because it's specifically this function, right? If we were approaching it from the negative direction, it makes negative infinity. I mean, it makes it kind of a negative number, and we don't really want that. We only want the positive one. And then now we're looking at this problem where it's the limit as x approaches 1 of the quantity 1 over ln x minus 1 over the quantity x minus 1. We do straight plugging in, what do we get, right? What is 1 over natural log of 1 minus 1 over 1 minus 1? Well, it's simply 1 over 0 minus 1 over 0, but we're approaching it. So like think of this being like 0.0000000, on and on 1, right? It's going to be a huge number. And if the closer we get to 0, the closer we get to this form, infinity minus infinity. And the reason why this is an indeterminate is because we aren't sure which one outpaces the other, right? Does the natural log go to infinity faster than the other one? Or is it the other way around? That's why we call it indeterminate. So we want to look at that. So now our goal is to try to manipulate it in such a way that we can get an indeterminate form that's a quotient, right? I think this is going to be side work, right? I think probably finding a common denominator and adding them together is actually pretty simple. So x minus 1. This is probably how we're going to go about. Oops, it should be like this, right? I have a common denominator, so I can equal that to x minus 1 minus natural log of x over natural, let me write it this way, x minus 1 natural log of x, right? We have it in this form, and now we want to look at that limit, right? We have to keep making sure it's in that indeterminate form, even in this format. So if we plug it in of this, let's see if we get indeterminate, a type of indeterminate form. Maybe we've seen it before. So we plug in 1, we get 1 minus natural log of 1, and a 1 minus 1 natural log of 1. This is in fact 0 over 0. This is an indeterminate form, so now we can officially use L'Hopital's rule, right? We just find the derivative of the top and the bottom, not too terribly difficult. So we have 1, that goes away, so it's minus 1 over x. And then this one, we have to use the product rule on the bottom. So it's x, I'm going to differentiate the ln x first, and then I'm going to differentiate the other term afterwards, which is just simply ln of x. And let's see if this works, if we just plug it in right now. 1 over 1 over 1, 1 divided by 1, 1 minus 1 divided by 1, plus natural log of 1. Well, this is 1 minus 1, which is 0. And then we plug in here, and this is still 0. So it's an indeterminate form. We can use L'Hopital's rule again, since it's in the quotient. So we're going to keep going. Limit as x approaches 1, and then we have to take the derivative. Okay, so the constant goes away, so it's actually just 1 over x squared divided by, right? This one's very weird. I kind of don't want to use the quotient rule, so here's some side work really quickly. X minus 1 over x is equal to x divided by x minus 1 over x, or it's just equal to simply 1 minus 1 over x, right? So the limit, so we want to find the derivative of this instead of this. I don't want to use the quotient rule again, so the derivative of this is actually the same thing, 1 over x squared, and then plus 1 over x. So I went pretty fast on that. Maybe if you really want, you can use the quotient rule, or you can go through this logic right here, where my cursor was at, right here. And then you can just find the derivative of that instead. It's so much easier to me, so there we go. So let's look at this one. If we find the derivative of this, what do we get? Let's just plug it in. Let's see, what do we get? We get specifically 1 over 1 divided by 1 over 1 plus 1 over 1, which is 1 over 2, right? Right, we just get 1 over that. So then the next thing is we basically found the thing. So our overall limit as x approaches 1 of what's the original function? It was 1 divided by natural log of x minus 1 over x minus 1. That was it. It's just simply 1/2, and I found that through multiple usage of L'Hopital's rule and kind of some algebraic manipulation to get it into a type of quotient. So that's the ideal process for dealing with these types of indeterminate forms. And that's it for this one. next time we're going to look at a different method to find different indeterminate forms and how to work with those. And it's a very interesting way to do it, to say the least. So that's it for this video.